the third row, you will have 0, 0, 2 minus 2, which is 0, 0, and 2. And this is very obvious that you don't have a consistent system. So if you look at this, look to the third row, there is no solution. Remark, you will have the coefficient matrix, all elements equal to 0, but the augmented matrix still have 2, so there is a mismatch in the ranks, as you know, blah, blah, blah. So it's correct. Okay, for the number D, if alpha equal to 0, beta doesn't equal to 2. Once more, I will need the echelon form. Guys, before we continue, remark for this question. You will have to get the correct echelon form. If you have a mistake with the echelon form, all the rest of the question is not going to be correct. So please do concentrate, step by step, easy. Repeat the signs. Look at it carefully. Once more for number D. If alpha equal to 0, so I will start replacing alpha by 0. Once you start replacing alpha by 0, you will have now all the last row is equal to zeros, and this is the form that you need. Beta doesn't equal to 2. Beta doesn't equal to 2, which means the rank will stay will be 3. Then the system is consistent and the underdetermined with a degree of interdependency of 2. No, this is not correct. This is it's going to be a consistent system, but underdetermined by 1. So half the result that is giving you is correct and the other half is not correct. Okay, all is true, but undetermined by 1, as I told you. So number D is not correct. The final result, or the final multiple choice question, is asking you about alpha equal to 1, beta equal to 3. Then the system has only the solution 7, -4, 3, and 1. And once more, I will need the echelon form, and I will start substituting. So this is the echelon form. I will replace alpha by 1 and the beta by 3. Once you do this, this is your matrix. Start to put it on the reduced echelon form in order to get a solution. So I will continue with a couple of steps. Okay, this is the next step, which in which we did use the last row, multiplying it by -1, adding on the second, and then by -2 and adding on the first row. And this is the final reduced form. For the final reduced echelon form, you will find that the solution set is -7, -4, 3, and 1. Comparing these results with what is given, which is 7, -4, 3, and 1. Please try to be careful about the signs. See, it is almost quite right, but just only missing the sign from -7 and the +7 will make this choice not correct. So, solve it as much as possible and be careful about the signs. So, number E, it is not correct, as you can see. As we did go through all the previous steps, see, bottom line, there is some questions you can answer easily from definitions, and the other questions need a huge attention. All the steps, everything should be in mind. This is one, I know you don't agree with me, but I love these questions. Here he's telling you, let A belongs to a square matrix 3 by 3. B an arbitrary matrix. So, actually you are not given A. A is not used. And consider that B is obtained from A by performing the following elementary row transformations. Stop. He's gonna play with you on the elementary matrices. So please try to get back to your elementary matrices and how to control them. Now, he's giving you that I have A, I will make a switch in rows, it's gonna be A1, then I will multiply by 5, third row, it's gonna develop A2, I will get third row plus 4, L1, and I will end up having B. Okay, if A equal to I3, so he's saying if A is a unit matrix, which is 3 by 3, then B is invertible. And the B minus 1 will be like this. So, what he wants me to do right now. Step-by-step solution for this problem. Leave the positive, the right or the wrong questions. I will go step by step. Now consider a matrix in the unit matrix, and it is an elementary matrix. Now let's do the recipe that he told you about. I will start with switching rows, first row and second row. So this is the first switch. Then I will start multiplying the fifth row, which is going to be 0, 0, and 5. Then I will multiply the first row by 4 and add it to the rest to the third row. This is matrix B. This is matrix B. So see, in number A, he proposed that A equal to unit matrix, and he started working his magic with the elementary operations to have the matrix which is B. So this is B. The question didn't end. He didn't ask you about B. He's mean about that. He's really mean. All he has to answer you is get the inverse of B. So I will start getting the inverse of B. How to get the inverse B? Do it the way you like it. But I would prefer Gauss-Jordan. So now I will start directly taking the matrix B, put it here on your left hand side, putting the unit matrix on the right hand side, and work your magic, baby. Work your magic. Okay, I will start by getting this right side to equal to a unit matrix, replacing rows, blah, blah, blah. You are better than me in all of this. This is the first step. The second one, as you can see, I've succeeded in getting the second column correct. I will go for the last one, so I will have to divide by 5. And this is the last one. So the inverse actually in the matrix on the right, this is the inverse, which is 0, 1, 0, 1, 0, 0, negative 4 over 5, 0, and 1 over 5. I will need now to check if this result is correct or not. How to check? Just simply compare this matrix with the multiplied elements or matrices that was given to you in number A. And yes, it is correct. So as you can see from this, just only one part, he asked you about the elementary operations. He made you getting a matrix from nowhere, which is beta. Then he also, within hidden, make you get the inverse of this matrix. And finally, to compare the multiplication of these three matrices with the final result that you have. And it's going to be correct, of course. Okay, once more about B, he's asking you the rank of matrix A is equal to the rank of matrix B. Of course, both ranks are equal and of degree 3. I'm sure about this because we did already the elementary row operations previously in step 1. This is matrix A and that's matrix B. Okay, before going to C, let's look at D. A equal to I3 and the B transpose will equal to all of this. Get the transpose of the B matrix. This is the B matrix is giving you above. All I have to do is to move the rows into columns and columns into rows, and then once more check this result with what's given. It's going to be correct also. For number C, all I have to do is to listen to him. I will start with matrix B, and I will do the row operations that he stated. Multiplying the first row by a quarter and adding it on the third row. Then multiplying the third row by negative over 5. So this is the result that you will have. Then L1 minus L2, and this is the final matrix. It's not what's given, so it's not matrix A, so it's not correct. Number E, he's asking you about these matrices, these elementary operation. If it was multiplied by A, it's going to equal to B. No, it's not going to be correct. If you try them, it's not going to be correct. Just multiply all of this times A, and you will find it not equal to B. So this question mainly stands for doing exactly the steps that you were asked to go through. Here's is asking you about identify the inverse of this matrix, and you can see that question number 4 doesn't have the triple sign, which means it will have just only one correct answer, and it's a very simple direct question. All I have to do is to get the inverse, and you know how to get the inverse in anyhow, either using the determinants of the adjoint matrix, or you can do it simply by Gauss-Jordan technique. So I have taken the matrix which is given. Please be careful about the steps here. I will need the first element to be 1. So simply replace the second row instead of the first and vice versa. Try to get the first column correct, which is 1, 0. Then start from the pivot, which is 1, getting 2, forcing the negative 2 to be 0 and the 4 to be 0, as we used to do previously. You will find your final result. This is the inverse, which is F, as you can see. A very direct question, and there is no ideas about how to go through it. Once more, in question number 5, is asking you to indicate which statements are true. If A is a square matrix, satisfy the equation A squared minus A equal 2I equal to 0, what the hell? Then A is invertible. So he is telling you that A should satisfy this equation. And from this, start to think how to prove that A is invertible. So the first question will need work from you. The second, for any matrices A, B, C, D, and X with A, B, and C invertible, if the equation is given, he's giving you an equation, and then prove that X equal to B, C minus 1. Okay, this also will need extra steps. I can't answer it like this. Look for C, a system AX equal to B, where A belongs to an n by n. Have a rank n is a consistent system. Okay, just wait. This is going to be an easy question. Just go through the dimension of your matrix. Okay, so the coefficient matrix is an n by n. The rank also equal to n, which means the augmented matrix also is n. That's, you will have a consistent system. So number C is correct. So if you have AX equal to B, where A belongs to n by n, remark that the rank is equal to n, which is the number of rows. That means you will have a consistent system for sure. Okay, so now I've gained that C, you can answer it right away. You don't have to do the steps. For number D, for any matrices AB belongs to square matrices, it holds that A plus B to the power of 2 equal to A squared, 2AB plus B squared. That's a complete rubbish. Why? Because you know multiplication matrices is not commutative. So also he's giving you within the lines also another question which is really very simple to have. If A belongs to an n by n matrix and it is an invertible matrix, then for any matrix B, the matrices B, the matrices B and AB have the same rank. Okay, let's break this step by step. He's giving you A, which is an n by n matrix, and it is invertible matrix. So A is invertible, which means it will have the same rank. Then for any matrix B, which is n times B, if you take a good look for A, which is n by n, and the n by B, look with me on the whiteboard. This is A, which is n by n, and that's times the other matrix, which is B, which is gonna be n times B. The result of these two matrices, once you multiply it, it's gonna be the same rank as B. So AB, it will be the same rank, which is n by B. So the last statement is correct. As you can see, there's some questions will need an extra work from you, and others you can answer them really very easy. Okay. So this is for number C, as I told you, and this is for number D, okay? And this is for number E. Yep. Okay, let's get back to number A. Number A, he's stating that if A belongs to an m by n, satisfy the equation A squared minus C equal to I plus 2I equal to 0. In order to do so, I will start with the following. I will make a small manipulation. Instead of proving A squared minus A from the given equal to 2I, I will put it in this manner. So it's an A squared minus A equal to negative 2IN. Let's get the inverse, let's get the determinant of this statement. Why to go through a determinant? Because determinants and inversion is connected somehow. You know that in order to get an inverse of a matrix, this matrix shouldn't be singular matrix, which means the determinant of this matrix shouldn't equal to 0. This is the point that I will use to prove this statement. So now once more I have a squared minus a equal to 2in. I've taken a as a common, so I have a times a minus I of n equal negative 2in. Take the determinant of both sides. That's the statement. I've wrote the statement for you. Okay? A matrix is invertible if, and only if, its determinant doesn't equal to 0. So now I will start. Take the determinant of both sides for the first statement. I will have determinant of a times a minus in equal determinant of negative 2in. Now once more, it's going to equal to determinant of a times determinant of a minus in. Determinant of negative 2in, it will equal to negative 2 to the power of n. So it's not equal to 0. Now, I will have determinant a times determinant a minus in equal negative 2 to the power of n. Which means that determinant of a, if it is equal to 0, then this statement will equal to 0. So that's a proof that the left-hand side defines that determinant of a will never equal to 0, which contradicts the meaning that they are already determinant of a doesn't equal to 0, and the a is invertible, as you can see. So once more, the main idea is just to break your problem. This is the given. Just put it on this manner. Now you have a new key. I know some of you will ask me, what the hell? How this gonna be in my mind? Before you solve this problem, it's gonna be difficult. But for the time being, I'm adding a new card with you to use once you need it. So once more, I will try to break it this way. I am taking advantage from the definition, one of the conditions for an inversion of a matrix. Then I will start with breaking this statement, determinant of a times determinant of a minus n. See how I took an advantage from the right-hand side, which is a determinant of negative 2in. And you know from the determinant properties that the right-hand side will equal to negative 2 to the power of n. As you can see in the first part of this statement, look to my hand, it's in here. Okay, so once more, determinant of a times determinant of a minus in, it will equal to negative 2 to the power of n. I don't care about determinant of a minus in, but I want to put the light on determinant of a. This statement indicates that determinant of a never equal to 0, which means a is invertible, and that's the statement for this problem. Okay, number B, it's a beautiful piece. Question number B. And it's really very simple. When you look at it and read it, it will be difficult. But once you start it, it will be very nice. It's all about multiplication. The second question, you will for any matrices A, B, C, D, and X, which are square matrices, A, B, and C are invertible if the equation B minus 1 CXA equal to T. I will start from the given. Start from the given, as I told you. That's B minus 1 CXA equal to D. I will multiply both sides in B from the left. If you multiply this statement in B from both sides, B will cancel B minus 1 and will be added to the right hand side. You will have CXA equal B minus 1, B times D. Then once more, I will need to move A or to get rid of A. So I will eliminate, I will multiply both sides, but from the right in A minus 1. So I will have now C of X equal BD A minus 1. Finally, I will multiply from the left by C minus 1, both sides, and I will have X equal to C minus 1, BD A minus 1. Now I've succeeded in separating X in one side. If you compare this result with the given result, you will find there is a mismatch. This is why B is not correct. Okay, it's really very close, but it's not correct. As you can see, he just switched C minus 1B from the given result and from the final result. Once more, I'm telling you this more than once, the exam is accessible, but it needs work, it needs focus, gathering your ideas, start to use them step by step. Okay, for the fifth question, he is telling you that, let's see, I'm sorry, we are on the same question. Of course, I did go through C once more from the dimension of the coefficient matrix and the rank. It is a consistent system. Number D for any matrices, expand the left-hand side, taking in mind that multiplication in matrices is not correct. So number D, it's not correct. Number E, you will have review the dimension of the given matrices, and it's really very simple as we spoke earlier and we did on the whiteboard. Now let's go to question number 6. Okay, number 6, it's talking about vector spaces. Okay, consider in each of the indicated vector spaces the usual properties of addition and scalar multiplication. So he will focus with you on building a vector space or a sub-vector space. So please go through them easily step by step. He's giving you F, which is the set A, B, C, D, which belongs to R4, such that A plus B equal to 0 and B plus C plus D equal to 1. This is not a subspace of R4. This will need some work. For number F, A belongs to an n by n, and the A equal to A transpose is a subspace of the matrices n by n. Also, I need to think about it, but I'm having the hatch that it's correct. Number F, it's A and A square, is a subspace of R2. Well, I'm suspecting this is not gonna end well. I believe that A square is not gonna be a sub-vector space, but I will prove it, of course. Any vector space E has a sub-vector space E. This is directly not correct, because a subspace, it's not an empty set. At least it contains the null set. So this statement, as I told you from the definition, it's not correct. Let F be a subspace of a vector space E, and let U and V belongs to E, and if U plus V belongs to F, and U belongs to F, then V belongs to F. No, this will need just a little bit extra work from us. Okay, let's go step by step. To check for a subvector space, remember, I will have to check 3 things. Number 1, 0 vector of R4 belongs to the subvector space. This is number 1. Number 2, closure under addition and scalar multiplication. Failure in any leads to not a vector space. So if you remark for the 0 in R of R4 for the first question, yes, the 0 belongs to A, B, C, D. So zeros, and let's see if this exists. For the first condition, putting A and B equal to zeros, it will develop a 0, which is correct. But this will be satisfied at the origin of R4. Taking the second condition, which states that B plus C plus D equal to 1, once you start substituting by B, C, and D equal to zeros, it's not going to equal to 0, which means that the second condition violates the meaning of having a 0 of R4 belongs to this subvector space, so it's not a subspace of R4, and that's the statement of this problem. Okay, so it is correct, of course, the statement is correct. Okay, so it's not a subspace. For question number 6, also, yes, I forgot to tell you about this. Guys, please, when you solve, sometimes I do this mistake also. I start a lot thinking about what he's giving me. Read the statement carefully. He's telling you that ABCD with this condition is not a sub-vector space of R4. And actually the proofs that we have that it is not a sub-vector space of R4, so that first statement is correct. Please be careful about these statements. It's really very tricky. Okay. Okay, let's go for B. Here he's asking you to check that A, if A equal to 2A transpose, this is going to be a sub sub-vector space of n by n. This is really very simple. All the conditions. The zero vector of square matrices belongs to the sub-vector space. Because you can have a matrix with all zeros from the dimension n by n, so the origin really exists. Any two matrices n by n in addition or scalar multiplication, they will exist in a square matrix. So actually number B is correct. Let's focus on C. C, so this is the statement, I'm sorry, of number B. This is the addition, the multiplication, so all set. Let's look at C. To check for a sub-vector space, you should check for a zero, closure under addition, scalar multiplication. Of course, this is not going to be a sub-vector space. The statement is like this. Let's consider U and V two vectors that belongs to F. So the first of them is A and A squared, the second is B plus B and B squared. If you get the addition of U and V, you will have A plus B, A squared plus B squared. But if you have the coordinates together, you will have on the second coordinate A plus B to the power of 2. And A squared plus B squared doesn't equal to A plus B to the power of 2. So it's not closed under the addition, so it's not a sub-vector space. For any vector E, as I told you previously, it has a sub-vector from the definition directly, not correct from the definition of a vector of a sub-vector space. It's not an empty set. For number F, okay, let's focus. To check for a sub-vector space, zero vector of square matrices belongs to the sub-vector space, closure under addition and multiplication of U belongs to F, so U and V belongs to F, B belongs to F. From the definition of the addition, mainly, you will find this statement. So it is correct. Now, consider the matrices A and B. Under these conditions, indicate which statements are true and which are not. He's telling you, consider matrix A and B, is giving you the matrices by itself. If the matrices A and B are both invertible, I will have to check. How to check? You can get the inverse of these matrices, or, wait. We can get the determinant. If the determinant of a matrix equal to 0, it will be invertible. If the determinant of the matrix doesn't equal to 0, doesn't equal to 0, it will be invertible. If it equal to 0, it's not going to be invertible. So all I have to do once more, to be invertible, the easiest way is to get its determinant. So I will get the determinant of matrix A, which is really very simple by Sarah's rule, multiplying negative 1 times 1 times 0, 0, 2, and 0, 2, 1, negative 1, which is going to come up to negative 2, minus, do the other side, you will have determinant of A equal to 2. While the determinant of B equal to 0, so the first statement is not correct. The reduced row echelon form of the matrix A is the identity matrix? Yes. Once the determinant doesn't equal to 0, you will be able to get a reduced echelon form to a unit matrix. So you don't have to do extra work. It's just from the understanding of the first one. For number C, he is giving you the system AX equals C is a consistent system for any matrix C belongs to a 3 by 1. Okay, let's read it once more. So A, which is invertible matrix, which means the rank will equal to 3, is a consistent system for any, yes, it's correct. You don't have to do any extra steps. It's actually from the first statement, it is correct. Number D, the reduced row echelon form of matrix B is the matrix, and he is giving you this matrix. Okay, once more, both on reduced echelon form, and the result will not be this matrix. So use matrix number B, start to do the reduced echelon form steps. It's not going to equal to this matrix. Determinant of A equal to 2, we already have this from the first step. So as you can see, this question is really very simple and very fast to answer. One of the things that I want you to put in mind, you have 10 questions in your exam. Some of them, they take time. Others, you can do them really, very quickly. And I don't want to say that it depends on luck, but start each question, read it, and don't worry about the time. It's already evaluated for you. Indicate which statements are true. The product of any two elementary matrices is also an elementary matrix. Let's think about this? No. Why it's not correct? Because simply, if you have an elementary matrix 4L1 plus L2 times another elementary matrix 5L2 plus L1 and you multiply them together, they will develop a non-elementary matrix. So the first statement is not correct. For a matrix A belongs to 3 by 4, there exists matrix B 3 1 such that 2 1 negative 2 1 0 3 is a solution of this system. This question is correct. Why it is correct? Because of the dimension. He's giving you A 3 by 4 times the solution is 4 by 1. So once you multiply, the result will be 3 by 1. So it's correct. And this is really a very tricky question. It will take time from you to think about it. It's really very direct. So number B is correct. Any matrix A3 by 4 times a 4 times 1 will develop a matrix 3 by 1, which is correct. The matrices. This is also a tricky question. And it's not nice, actually. Number C. You will have to think how to start from one of them and reach the other. It's giving you 1003, 0012, and 1039, 1015. These questions are not difficult, but it needs time, and it will depend on your luck. I started from the second one. I will tell you about this proper. I will start from the second one and start doing the following. Multiply the first row by negative and add it on the second row, Then multiply the second row in minus 0.5. Then add the second row on the multiply the second row in negative 3 and add it on the first row. I've written for you the recipe. Just do it, and it will be you will be able to get from the second matrix to the first matrix. The last question, okay, the identity matrix of order 3 is not an elementary matrix, it's not correct, direct. It's an elementary matrix. So number D is direct. The identity matrix of order 3 is not, no, it's an elementary matrix as I told you, so this statement is not correct because of the not words that exist in it. If you look to problem number E, all I have to do is to expand this determinant, which is a 4 by 4 question, 4 by 4 determinant. I would prefer just to seek the row or column with the maximum number of zeros. So I would suggest that you expand this determinant at I, the fourth column, and then start by 3 by 3 and so on. And you will have, it's not correct, the exact values, it's going to be negative J, I, A, and D. So once more, it's really very simple. If you want to do it, I will start with, of course, the rule of sign, which means I eliminate row and column. So if I eliminate the row and column, I will have A, 0, and 0 for the first row. Then I will have C and D and 0 for the second row. Then I will have 0, 0, okay, 0, 0, and J for the last column. Once more, expand on J, so you will have A times J. Eliminate the row and column, you will have A, 0, C, and D. Once you try to expand this, you will have I and J, and this is A times D, as you can see, but with a negative sign. So you will have almost the same, but with a different difference with negative sign, as you can see. So this is for this question, which is question number 8. For question number 9, is giving you A, which is 3 by 3, such that A adjoint A equal 4, I3. Okay, this is very close. Okay, the matrices A and the adjoint A are not both invertible. Okay, let's see. A first statement is not correct simply because if you look to the given, which states that A adjoint matrix equal 4 of I3, if you multiply then A minus 1 both sides, you will find that A minus 1 already exists, the determinant equal to 4. So the first statement is not correct. A is invertible by itself. And once more, be careful about rejecting these tricky questions. For number B, the reduced row echelon form. So once more, this is the statement as I told you. Just manipulate the level. You will find that A minus 1 equal 1 over 4, the adjoint A, and the determinant of A equal to 4. The reduced row echelon form of the matrix of algebraic complement. Oh, wait, what's the algebraic complements? Huh? Do you remember? The algebraic complements are the cofactors, okay, of each element of the elements of the matrix. So the algebraic complements is the cofactor matrix. Since A is invertible, then reduced echelon form is of third degree, so it's correct. The matrix adjoint has a rank of 3, of course, because it's already invertible. A minus 1 is invertible. So with determinant doesn't equal to 4, so the adjoint is going to be of third degree. The determinant of adjoint A equal to 64, this is not correct. Start from the given, which is get the determinant of A times adjoint of A. Determinant of A equal to 4. Determinant of adjoint of A from the definition is going to equal to 4i3, which is going to be 46. So divide by 4, the actual value is 16. So the determinant of the adjoint is equal to 16. The matrix A is invertible. Determinant of A equal to 4. Determinant of A minus 1 will equal to 1 over 4. So the last question is correct directly from the beginning. Now for the final question in this exam, and question number 10. Let A, ABC, D, E, F, G, H, I, which is the matrix 3 by 3. Determinant of A equal to beta and doesn't equal to 0. So as I told you, focus on the lines. You are giving the matrix and it's a determinant. Under these conditions, let's look to A. We here in A is giving you 2A, 2B, to C, just a second, 2A, 2B, to C. So we multiply the first row by 2, we multiply the second row by 3, but we replaced the second row and third row. And for this,